All right. Hello, folks. So we're back to the second lecture, which is on vectors. So make sure you watch the previous video, the 12.1 on the three-dimensional coordinate system. And today we'll talk about vectors. Okay. So first of all, I'll make a very vague definition here. A vector, you can place them in R, in R2, or R cube. So it is basically on a line, or on a plane, or on a three-dimensional coordinate system. So a vector is a quantity that contains two information. One is the magnitude, and one is the direction. So that's a definition that doesn't work on any level. Basically, a vector is a arrow. It connects two dots. So say we have dot A and dot B. Then this arrow is called a vector. The information of magnitude is contained in the length of this segment. And direction is simply A towards B. Okay? So in short, usually we denote the vector V by AB. Note that AB is not equal to BA. There's a direction difference. AB is not equal to BA. Okay? Those two vectors share the same length but opposite directions. So be careful with the notations. They are different. And there are very many different notations about vectors. Sometimes people write this, which is what I wrote here. Sometimes people write this, and sometimes people use both letters. So it depends on the content. But throughout this lecture, I will try to use this notation. Okay, a letter with an arrow. Okay, so that's what a vector is. And to define more precise in terms of the algebraic language, we usually do this. If A is given to be the point x1, y1, z1, and B is given to the point x2, y2, z2, I will demonstrate for the three-dimensional space, but the two-dimensional space and the one-dimensional space work similarly. So the vector characterizing the direction from A to B will be denoted by V equals to AB equals to the difference between x2 and x1, y2 minus y1, and z2 minus v1. So be careful about this. This is x2 minus x1. So we're subtracting the starting point from the terminal point. It is B minus A, not A minus B, okay? B is the terminal point and A is the starting point. We subtract the starting point from the terminal point. So then we get a direction from the starting point to the terminal point, okay? So that's the definition of vectors. Now, basically, given those definitions, we can define some algebra on the vectors. And there are two specific algebra that we can define on vector. One is called vector addition, and one is called scalar multiplication. So for addition, we're adding up two vectors. So given a vector u, given by this coordinate system, and given a vector v, given by this coordinate system, x2, y2, z2, then their addition is simply adding up them entry-wisely. So you add up x1 plus x2, you add up y1 and y2, you add up z1 and z2, okay? And then you form a new vector, which is called u plus v. This diagram might show how that geometrically means. So if you have this vector u going from, say, point A to point B, then if you want to add some v going from point B to point C, then the additional vector is simply connecting the starting point and the terminal point, sorry, the starting point of the first vector and terminal point of the last vector. So AC will be our new vector u plus v. This type of argument is called triangular law. And you can draw a similar diagram like the right-hand side here. So if you have have two vectors, u and v, and given the same starting point with different terminal points, then somehow you can try to shift this thing, the v, up to here and connect the terminal point and the starting point. So basically, after having u and v, you draw a parallel, you get a parallelogram. Then the line connecting diagonal pointing from this starting point to this terminal point will be our additional vector. Okay. So for example, you can try it by yourself. If this is 2.212, if this is 313, then you can try to picture them on the 3D coordinate system. And this should be 5 to 5. Okay, the difference. Right. So those are the addition of vectors. So again, let me remind you, addition of vector is a vector plus a vector. Okay. And now we're dealing with scalar multiplication. So just what it sounds like in its name, it is multiplying a vector with a scalar. So basically, a scalar is just a number. That's what we understand it to be a scalar. So given a scalar v, x, y, z, given a c, a scalar, then a scalar product of c, sorry, that's not a good name. The scalar multiplication between the scalar c and the vector v is simply another vector, which is denoted by cx, cy, and cz. Okay, these are just usual multiplication. So for instance, 2 times 2, 1 is simply 4, 2. Okay, that's the definition of scalar multiplication. So again, addition of vectors is vector plus vector give you another vector. And scalar multiplication is a scalar multiplied by a vector gives you another vector. Okay. And geometrically, what does scalar multiplication means? For example, if you have a positive scalar, then you're either elongating your vector. For example, in this case, it is v to 3v, or you're shrinking your vector. So maybe v gives you half v. And if you have a negative signature on the scalar, then you're reflecting that vector. So if it's v, then this might be minus half v. The length is shortened down to half, and the direction is opposite. So those are the algebraic vectors and their geometrical meaning. Okay. And naturally, one can define the subtractional vector via what we just defined. The subtractional vector is basically u minus v is basically u plus minus v. So we have defined what is a scalar multiplication, right? That is okay. So this is another new vector. And we have defined addition. So that's basically everything. And geometrically, what does this mean? If you have u and you have v, okay? Now, what is u plus v? Sorry, what is u minus v? So u minus v is something that looks like this. Something add up with v will become u. Okay? So see that if this is a starting point of u, and this is the ending point for u, right? So if you want to add up v and add up the vu, then this should be ru minus v. Okay? So be careful with the subtraction and addition. They are different things. And try to draw the diagram down so you guys can have a better understanding of how those algebraic definition affects the geometric meaning. Right? Try to do the suggested assignment. I think there's several of them is trying to draw the diagram of the vectors. Okay, and here are the properties of vectors. There are 8 of them, and they're mostly quite direct. This is out of scope, but basically we list out these 8 different properties of vectors as an axiom. So we, in more advanced math, we try to use this 8 different properties to define what a vector is. But for now, it is a property. It is a consequence of our definition, okay? So first of all, u plus v is v plus u. That's quite direct because summation is always commutable, right? 1 plus 2 is equal to 2 plus 1, so that's okay. And you have associative. So adding up the first 2 and adding up first the last 2 does not affect the summation. So the order of a summation does not affect the result of a summation, basically. And identity, so I will denote here the 0 vector to be 0, 0, 0, okay? And I'll use that for the rest of the course. So of course, v plus 0 will be v, just as in the numbers. And v plus minus v, so go this way and then go this way, then it'll be 0, right? And this is a little bit more sophisticated. So v times v, this is a scalar multiplication. This gives you another vector, right? And then multiply by a, which gives you another vector. And this vector will be the same as you multiply this 2 first. So a times b is the usual number multiplication, which you learn in elementary school. 2 times 4, 4 times 6, something like that. So this is the usual number multiplication. And this tells you that, again, is in some sense, the scalar multiplication and the multiplication number is commutable. You can first compute the number, and then you compute the scalar multiplication. Or you can compute the scalar multiplication iteratively. For a sixth probability, you have 1v equals to v. So this one will be a number, okay? 1 is a number. 1 times v is v, which is the same thing as a number algebra, right? And you have several distribution laws. So for a scalar, a plus b, if you do a scalar multiplication between this summation with v, then you get av plus bv. The same thing happens for the distribution over vectors. So a is scalar, taking scalar multiplication with u plus v, you get au plus av, right? Let's do some example here. Say we do the 7 as a proof. So most of the proof are straightforward. I just demonstrate this here to show that in some sense it's not that direct, but we have to see like how each step proceeds. So you see that we are calculating a plus b multiplied by a vector, right? So by definition of scalar multiplication, we want to multiply each entry by this number, which is a plus b v1, a plus b v2, and a plus b v2. Now, by the distribution law of number multiplication, which you learn in elementary school, 1 plus 2 times 3 will be 1 times 3 plus 2 times 3. So a plus b v1, now that is a commutation of numbers. So you get AV1 and BV1, AV2, BV2, and AV3 and BV3, okay? Now, by the definition of vector addition, this is equal to this, right? Because vector addition is simply summing up each entry entry-wise. And then lastly, by definition of the scalar multiplication, this guy is AV and this guy is BV, right? So you see that there is a little bit nuance here. So first you apply definition of the scalar multiplication. You also apply definition of scalar multiplication here. And then you apply the definition of the additional vector here. And this simply follows by the distributional law of real numbers, of how we calculate the usual numbers. All right? This shows that a plus bv will equals to av plus bv, which is our seventh rule. This here is not really important because most of them are really intuitive. So just perform everything as usual, like what you have done in elementary school. You have everything that works in numbers also works in vectors. Just entry-wise. Okay, now we are into something more interesting, which is the norm or the magnitude. So we define the norm or the magnitude of a vector to be v, taking two vertical line here, 1, 2, 3, 4, like that, to be defined as you squared each coordinate and then you take the square root. And the definition of that is quite straightforward. Why do we define that? Basically, that norm simply reflects the length of this vector, the length from A to B, right? So if you recall from our last course, which is the three-dimensional distance, if you want to calculate the distance between 2 points, then you subtract those 2 points, and then you square those 3 entries, and you take a square root, right? And that is exactly what we have done here, right? The norm or the magnitude of V is simply the length of AB. So the norm of the V matches up with the length of the segment between AB. Right? So that's the definition. And in particular, when a vector, sorry, I should put a arrow here, my bad. So don't forget, a vector is a vector, and the magnitude is a number. So after taking magnitude, you get a number. Now, if a vector has magnitude 1, now we call it a unit vector. Just a noun to describe a vector of unit 1. Right. So now let's try to do some examples. Say the vector u is of coordinate 2, -1, 3. V is of coordinate 3, 2, 4. We want to find this guy. So let's do some vector calculus first. So what is 2u? Oh, let me use black to be consistent. 2u plus minus v. So everything just happens entry-wisely. You have 2 times 2 minus 3, 2 times minus 1 minus 2, 2 times 3 minus 4. Okay? The first time here, 2 times 2 comes from the x-coordinate. This comes from y-coordinate. This comes from the z-coordinate. And similarly, minus 3, 2, and 4. So we end up with the vector being 2 times 2 minus 3 is 1. And you have minus 4. And you have 2. Okay? 1 minus 4, 2. That's the vector that we get by doing the algebra 2u minus 1. So what is the magnitude of this vector? It is simply 1 squared plus minus 4 squared plus 2 squared. So that's the length of this vector, or the magnitude, or a norm, which you get 1 plus 16 plus 4, that's 21 square root. Okay? So we will say that the norm, or the magnitude, or the length of this vector is 21, root 21. So you see that there might be different vectors with the same magnitude. For example, the easiest one, say 1, 0, and 0 minus 1. This thing has magnitude 1 squared plus 0 squared, that's 1. This thing has the same magnitude. So they're of the same magnitude, but they have different directions, right? So that's why I mentioned that a vector is basically a quantity that contains two different information. One is the magnitude, and one is the direction. So in here, we first tell you how to extract the magnitude information out of the vector. Basically summing up the square of each coordinate and then taking square root. That is the magnitude. Okay, and there are certain properties about magnitude again. And as I mentioned, usually this will not be that important. The important part, the proof is not important, but the important part is the application, how you apply those concepts, the theorems on the exams and on the examples. So in here, I want to mention that whenever we have two vectors, UV, in this case, I put it in R3, but R2, R1 works the same, and A is a scalar. So let me recall this once again. This thing means belongs to. So the first sentence is saying that let U and V be a three-dimensional vector, and A is just a number, okay? Then I claim two things, which is how magnitude play with respect to the algebra of vectors. So we have done two different types of algebra, right? One is addition, one is scalar multiplication. And this proposition tells you that with respect to addition, you have sub-additivity. Being precise, the length of u plus v will be less or equal to the length of u plus length of v. Okay. And secondly, respect to the scalar multiplication, it's actually really nice. The scalar multiple of u taking length will be the absolute value of that number a multiplied by the length of u. So see that since length is always a positive number, so it does not depend on whether a is negative or not. And this kind of reflects what I drew here. You see that if we multiply v by 3 times, then you get a vector which is 3 times log of v. If we multiply a vector v by minus half, we get a vector which is half times log of v. And we do not care about direction in this case, right? So that's two propositions. That's how magnitude plays with the algebra of vectors. And I mentioned here that what does this sentence mean? It means that when does the equality happen? The equality only happens when u is CV, meaning that u is parallel to v. Okay, so see that, for example, u plus v, then the new vector u plus v will be exactly the same. Sorry, we'll be having the exact same length as u and v. Sorry, the length of the new vector u plus v will be having the exact same length as the length of u plus the length of v, right? So that's the only case that happens, the equality. In most cases, it is strict inequality, okay? The first proposition here is not really useful. I just mentioned here for completeness. The second one is more important in our textbook. Okay, so again, for completeness, let me go through the proof real fast. The first item is actually quite straightforward intuitively. So you have u, you have v. Then, as I mentioned before, by applying the triangular law, you have u plus v being this vector by connecting the starting point of the first vector and the ending point of the last vector, right? That's u plus v. Now, the length of here is length of u, magnitude of u, magnitude of v, and magnitude of u plus v. Now, we all learned in, I think, high school or junior high that the third side of a triangle must be less or equal to the sum of the other two sides, right? So that directly gives you this. The length of one side will be less or equal to u plus v, okay? And we can actually prove it out algebraically, but that will require some work, and it relates on something that is called the Cauchy-Schwarz inequality, which, if I have time, I can post some videos and some note on Canvas, okay? But for now, it's not a full concept. It is completely fine if you are not okay with this. The second part is important, and it is actually simpler. So for the second part, if we're, oh, why did I use u? I should use v, but anyway. So if we're calculating the magnitude of a vector u, taking a scalar multiplication with a, then by definition, we get AU1 squared plus AU2 squared and AU3 squared, right? We can factor out a squared since those three have the same factor. And a squared can be factored outside the square root, right? Be careful, the factor of the square root of a squared is not a, it's absolute value of a. For instance, minus 3 squared is not minus 3, but 3, which is absolute value of minus 3, right? And then by definition, that is u. So you get the length of a scaled vector is simply the length of the vector scaled, okay, with the same constant a. Okay, so in particular, this kind of property tells us that we can normalize a vector, meaning that we can divide a vector by something so that that vector have a unit length. Being precise, given any vector u, by dividing its magnitude, this guy always has magnitude 1. Now, why is that the case? So let me go through this real fast. If we're calculating the length of this guy, right? The length. Then note that this is just a number. Be careful, this is just a number. So let me write it down slowly. Basically, this is saying something like this, right? This is our a in this case. We're multiplying a u by some scalar. And then, as I mentioned, we can factor the scalar out, leaving u inside the magnitude, right? And then you get 1. So this is called a normalization of u, meaning that it shares the same direction with u, but we normalize it to length 1, okay? So this is exactly what contains the information of direction. So you see again, you might have two different vectors which shares the same normalization, right? However, those two can have different magnitude, right? But that information is not disclosed here. So this thing contains exactly the information of direction inside the vector. So to be precise, given vector u, given it, how do I make it back here? So given a vector u, the information of magnitude is given by the length, or it's given by length or given by the norm. And the information of the direction is given by normalization of that vector. Okay. Right. So in practical, how do we do this? So for this example, I want you to find a unit vector that has the same direction as 1, 2, minus 3. So as I mentioned, to find a unit vector that has the same direction, basically you just normalize the vector. And by normalizing, I mean divide that vector by its norm or magnitude. Okay. So first of all, what is the magnitude of this vector? 1, 2, minus 3 to get 1 squared plus 2 squared plus minus 3 squared, right? And that gives you 14. So the vector that we are looking for is simply to divide each entry by 14, root 14. Then you can compute yourself. This vector indeed has magnitude 1. Okay, it is a unit vector in our previous language. Unit vector is any vector with magnitude 1. Okay, right. So that's all for the magnitude. Now I'll introduce something very useful in physics, which is the standard basis. So in most times, there will be a lot of different vectors, but they can all be reduced into some certain components. And by doing such decomposition, we can understand the physical or mathematical meaning more clear. So yeah, that I'll define this. In R2 space, we define I vector being 1, 0, and J vector being 0, 1. So this vector is I, and this vector is J. And in R3, we define IJK. One is correspond to the x-axis, y-axis, and z-axis. Okay. So note that I use hat here, right? Usually we all use hat to represent something which is of unit norm, which is norm 1, which is magnitude 1, which is a unit vector. But you don't have to use my notation. You can write something like this. Maybe it is more consistent. I prefer I hat to represent this kind of basis, but it depends on you. I would say that this and this both works. Okay. Right. So those are called standard bases, and let's see for an example how powerful this kind of decomposition is. So this is example 7 from the textbook. You have a diagram which has net force 0. That is, it is stopped there. It is stabilized. So you have two strings, one with angle 50 with the roof, one with angle 32 with the roof, and you have something there. It is 100 pounds. And obviously the rope or the strings provide some sort of tension force to grab the object above, right? To make it float here. So how do we calculate the vectors T1 and T2? So T1 and T2 are forces, and those forces go this way and this way. So actually we already know the direction. The direction is this way and this way, right? Basically. Now we are interested in the magnitude. How tense is this rope and how tense is this rope? Okay. An idea of standard basis comes in use. So we want to decompose everything in terms of the horizontal basis and the vertical basis. So let me explain what I'm saying. You can actually make the diagram in a more clear format like this. So first of all, you have an object which is of 100 pounds. So that vector is going downward with the length of 100. And you have another tension that is going, I read it as T2, T2 going this way, T1 going this way, with this angle being 32, this angle being 50, right? You have this angle being 32 and this angle being 50. So we already have the directions. And now to decompose the horizontal and vertical forces, respectively, you get if this is of length T2 as a definition, right? That is the definition of the magnitude of a vector. You can project them into the horizontal and the vertical components. And you can do that by applying the trigonometric function. So recall that say, okay, opposite divided by hypotenuse is sine, right? So this thing, say it is x divided by the hypotenuse. In this case, it is the tension force of T2 is sine of 32, right? So the vertical component of T2 is simply T2 times the magnitude of T2 times sine 32. And you can get the rest of the thing similarly. You have the magnitude of T2 times sine 32. Oh, sorry. This should be cosine 32. And you have a similar argument here, which you get sine 50 times tension of T1, cosine 50 times tension of T1. How is this useful? So now we only split everything in two directions, right? And since this is a net force zero system, meaning that it is stable, so every force should cancel out. And by writing things in terms of the ij component, which is the vertical and the horizontal component, you can simply analyze those two directions. So let me make this clear. What we have done here is that, let me use black. What we have done here is that we have decomposed T1 into two directions. One is the vertical direction. Oh, sorry, this is the horizontal direction. And this is going negative, right? Say we define left to be negative. So we're going leftward, which gives you a minus sign. Be careful about this. And I. Remember I is 1, 0. 1, 0, 0, 1, 0. In this case, it's two-dimensional, so it's 1, 0. Plus, we're going upward, right? T1 sine 15 J. Okay, so you see this vector will be the addition of this vector and this vector, right? Similarly, we have T2. Now you have positive because you're going rightward. T2 cosine 32 I plus T2 32 J. I'm not sure you guys familiarity on like a bunch of notation coming in and out, but let me explain this term by term. So this are numbers, okay? This is actual numbers, and these are vectors. So we're actually doing a scale multiplication and then adding things up. So we're scaling the horizontal unit distance 1, 0 by this number, which gives you this vector. And this number multiplied by the vertical unit distance, unit vector, gives you this vector. Adding those up, you get V1, T1, okay? And similarly for T2. Right, so now the main concern is to find the tension, which is T1 and T2, the magnitude of T1 and T2. So then we can list out the net force being 0 equation. So basically, we're trying to solve T1 plus T2 plus W is nothing. It is 0 force, okay? But in general, that'll be a more difficult equation to solve, so you can decompose things in which I just mentioned. So this equation tells you that both the horizontal and the vertical component of the vector should be 0. First of all, what is the horizontal component? What are the components? You have this guy and this guy, right? So minus T1, this magnitude, plus T2, cos 32 is 0. Okay? In this case, it is a, perhaps let me write this. This I is 0 vector. Okay? And similarly, you have T1 is going upward, sine 50 plus T2 cosine, oh, sorry, it should be sine 50, sine 32. And going downward, 100, J is 0 vector. Actually, let me use a different bracket. Okay, so basically we're simply saying that this guy should be 0 and this guy should be 0. All right, and you can solve whatever, however you want. Let me quickly go through how to solve this, which I believe is quite simple for most of you guys. Say this is 1, this is 2. Um, okay, let me exchange this to diagram so I have a better space on writing this. Let's put this here. Sorry for that. Let's put this here. This is our decomposition. This is our equation. Okay. Say we multiply. I'm using the cancellation method. You can use substitution or any method you like. Say I multiply this by sine 50 and multiply this by cosine 50. You get the same thing here. I'll just drop the vector part, okay? Because this does not really give you anything. We're just stating that the component here is 0. So you get sine 50 plus this guy times sine 50, and that's 0. Similarly, you have T1 sine 50 cosine 50 plus T2. I would recommend you try to keep the algebraic thing algebraic, meaning that don't try to type in the calculator for now. First, get the expression for, in this case, T1 and T2 in terms of some algebraic representation, and then type that representation inside the calculator to try to formulate a sense of doing algebra. Okay, so we get cosine 50 equals to 0. Let me go downward. Oh, I forgot the 100 term here. So 100 cosine 50. Okay. How is this useful? So the idea of doing that is that we can cancel out one of the terms. And in this particular case, the term that we can cancel out is this 2. Okay. And for T2, we have this big coefficient. Please let me know if this seems a little bit hard for you. I can recommend you some videos or exercises, okay? So in particular, you will get T2 being the whole thing here in the denominator, where a numerator is this guy. Okay? If you want to be a little tricky, you can do something like this. For example, this seems like a summation of angle, right? This is a sum formula. So this is actually equal to sine 82 degree. Okay, so that's all. And I have calculated this previously. This should be 64.91. Okay, our unit should be pound. So tension on the second string is 65 pound. And you can calculate T1 by, say, substituting T1, T2. So perhaps we substitute in this thing here. Then you should get T1 will be 6. Let me write notation. T2 multiply here. Cosine 32 divided by this guy. Divided by cosine 15. Okay. And let me see my answer. Just to make sure. See. Right. So it's approximately 85.63. Again, it's pound. Okay. So given that you have this net force zero diagram, and this object has 100 pounds of gravity, then the tension of T1 and T2 given this angle will be something like this. This is the magnitude of that vector. And we already know the direction, so this is what we need to find. Okay, let's go back a little bit. So I hope that is not too fast. For this class, we have defined what is a vector. Basically, it is a thing that contains two information. One is the magnitude, one is the direction. And we have seen that to precisely define the magnitude, you simply find the norm length of the vector, right? And to do so, you simply square all components and take the square root. And for direction, it is simply the division of the vector by its magnitude. It becomes a unit vector. We also define something like algebra of vectors. We know how to add a vector with vectors. We know how to multiply constant with vector. Okay, we have yet learned how to multiply vector and vector. That will be a different subject. But for now, we know how to multiply constant and vector, a scalar and vector. And geometrically, additional vector is connecting the starting point of the first vector and the ending point of the last vector. Geometrically, scalar multiplication represents that you either have a vector in the same direction or opposite direction with a length given by the absolute value of the scaling constant c. We have some properties of vector addition and vector scalar multiplication, but those are really straightforward. And this is what I just mentioned. You can calculate the information of magnitude through extract from a vector through computing this Pythagorean thingy. And you have a really nice property, which is that whenever you are scaling a vector, the magnitude of that scale vector will be equal to the magnitude of the vector scaled with the same thing taking absolute value. Yeah, last but not least, we have learned that you can always make a unit, which in this case, this thing contains the direction information of that vector, because you can have different vectors with the same normalized vector. Okay, and to do that, you simply divide everything component entry-wisely by its magnitude. We have a final example, which is stating how it is useful to decompose everything in terms of the center basis, which is ijk. I represents the x direction, while j is the y direction, and z is the k direction. K is the z direction, sorry. Yeah. So the reason to do that is that we can decompose everything in terms of either 2 directions or 3 directions, and then we can do algebra on each of the directions. For example, in this diagram, we see that we can decompose T1 and T2 in terms of x and y direction. And then by the net force zero equation, we get that the horizontal component of force and the vertical component of force must both be 0. And then we get a simultaneous equation, which we can solve using simple algebra. And then you can figure out the magnitude of T1 and T2. Right, that concludes our lecture for 12.2. Please let me know if it's going too fast or if you have anything that is not really understanding. Thank you so much. I will see you guys in the third video.